Hi, I'm Kevin from Keen Mass Appraisal Consulting. I'm here today to talk about the decision to use one model or many models. So it's just some perspective. There's been a lot of discussion about whether it is better to use one model or multiple models for an inventory. When I was starting out, I heard arguments from well-respected modelers on both sides. Over my years as a practitioner, I had to consider this question many times. Some practitioners will use only one model to predict values for a wide range of properties, perhaps for all camp properties within the jurisdiction. Other modelers use separate models for each of many subsets of properties. This session will present both sides of the one model versus many models argument and examine decision points that you can use to determine the optimal number of models you need. In general, who prefers to use more or fewer models? I have noticed that academics, cost modelers, people who run large AVMs, and some consultants prefer to use one model for all properties or a very small number of models for all properties. But I've also seen a lot of county and municipal modelers and many other consultants who prefer to use many models or separate models for each of many subsets of properties in their approach. So let's start with what are the decision drivers? Well, the more homogeneous your inventory, the easier it is to use one model. In counties with a lot of variation in any inventory, performance tends to increase with more specific models. How many modelers do you have? If you don't have enough manpower to build and maintain a large catalog of models, you may have to make do with using fewer models. How many observations do you have? Every model requires a minimum number of observations. The number of models that you can build may be limited by the amount of available data. We had plenty of observations in Philadelphia to support many single-family models, 16 in fact. But we had to combine several large areas of the city in order to support models for vacant land. The number of available observations forced us to use fewer models. Does everything conform to one time trend? You don't want subsets of properties that are subject to different time trends in the same model. Do all attributes behave the same way across the inventory? As with time trends, you don't want to combine subsets of property where the same attributes have different contributory effects on value into one model. So for instance, if garages add a lot in the center city model, but almost nothing in the more suburban type areas, you wouldn't want to mix those two areas together because then the model won't be able to make sense of your garage coefficient. And what it will do instead is push explanatory value that should be in the garages into the neighborhoods. And you probably don't want to do that. How consistent is your data quality? Data quality is the #1 issue with model performance. Want better models? Feed them better data. But if data quality is inconsistent, splitting the load across many models can mitigate or limit the effects of poor data quality. And lastly, how is your model structured? Some model structures can handle more variance in property types than others. And you can combine different subsets of the markets more easily, say in nonlinear or in AI models or gradient boosting models. So let's examine the case for one model. For one thing, it's much easier to build and maintain a smaller number of models. It's very easy to get overwhelmed especially if you're a small shop with trying to build or maintain a large catalog of models. With one model or a small number of models, you're going to have fewer coefficients across the entire inventory. So if my city looks like this and I could possibly have 16 different models, one for each area, I'm going to have a lot more coefficients in total. If I have one model, I'm only going to have one coefficient, say, for central air. If I have 16 models, there will be 16 different coefficients. It's going to be easier to have all of your attributes represented with a smaller number of models. And it's going to require, in total, fewer observations because you are going to have fewer variables and all the observations are being lumped into one file. It's good if you have a homogeneous inventory. So if you're in a suburban county where it was mostly built after World War II and there's not a whole lot of different property types or a lot of variance within the inventory, you can easily do the entire inventory with one model. Now let's look at the case for multiple models. Attributes that are significant in one model might be insignificant in another, so attribute significance may vary greatly across different models. Coefficients for each attribute will be more finely tuned with multiple models and therefore more accurate and precise. Separate time trends for each model. If there are multiple time trends in effect, you can have greater specificity within each model. The base property will be different in each of many models, and the combinations of attributes over which adjustments are compounded will also be different. If subsets of the inventory have different levels of data quality, the distortions will be limited to those models instead of degrading performance for all cases. Let's consider representation. Sample size and representation. Do you have enough observations to support more than one model? Some counties only get a couple dozen sales a year. That's certainly not going to be enough to support multiple models. Are all classes of property adequately or proportionately represented? So there's a relatively uncommon but very significant type of property in Philadelphia, and that is it's a one-story row house. They're very small, and they can only be found in these areas of the city. So in one model, we would have 12 observations, and that would probably be enough to develop an adjustment coefficient because it's a very strong and significant effect. But in multiple models, I would not have enough observations in any one of them to develop a coefficient. So I'd have to wind up treating them either like the base property, which would be wrong, or I'd have to have some kind of special code to handle them, which is kind of difficult because now it's subjective. It's not totally driven by data. Your coefficients can easily become confused when you're only using one model. So attributes may not be viewed the same way across all submarkets. When an attribute behaves differently in subsets of the inventory, is it appropriate to use one model? Or will the resulting adjustments be inaccurate in all cases? So here's a table that compares the relative importance of size adjustments, garages, spatial attributes, and property types from 4 different models that we actually ran in Philadelphia. So in Center City in the Northeast, here and here, you can see that there's a preference for smaller houses. But in South Philadelphia and Northwest Philadelphia, it's exactly the opposite. The premiums are for the larger homes. A detached garage in Center City is worth 10 times as much than it is in the far Northeast. The spatial attributes that are significant in each area differ from model to model. as does the most desirable property type. So combining these attributes in one model will still yield adjustment coefficients, but they will be less accurate than the specific coefficients that would be developed from multiple models. Mixing markets. When buyers' motivations or the attributes that are significant vary across subsets of the inventory, is it appropriate to try to use one model to capture the behavior of those attributes? So let's look at three very different markets. We have a vacant land market, a single family market, and a small multifamily market. That's 2 to 4 unit buildings. Some practitioners would combine all three into one model. But let's consider, who are the primary buyers in each of these markets? Well, for vacant land, it's going to be a developer, primarily. For single family, it's going to be an owner-occupant. And for small multifamily, it could be an owner-occupant or a small investor, somebody who's going to live in one unit, rent the others out. So their motivations are going to be very different. A developer is going to be motivated by profit, bottom line, and that's going to make different decisions. That person is going to make different decisions than somebody who's going to be occupying the property. For single family and owner occupants, it's a quality of life motivation, which is why they buy a particular property. For small multifamilies, it's a combination of quality of life and profit or affordability. And going even further, what are the significant attributes for each market? Well, for vacant land, it's going to be lot size, zoning, what are the permissible uses? Are there already entitlements with the property, or do you have to go through the cost and expense and time of getting the entitlements to build? What's the topography of the property? Now, in our single-family models, the only one of these elements that's even in those models is the lot size. The other three, zoning, entitlements, and topography, don't even get considered. In single-family, the strongest variables tend to be the improvement of the property type, improvement condition, and building size. So in the vacant land, there aren't any of these elements. If I look at small multifamily, the most important attributes are going to be the number of units, the overall building size, and what are the potential rents. So each of these markets demand something that the others do not have. So if I try to put them together in the one model, I mean, make no mistake, you will get results if you mix these markets into one model. But the reliability and the precision of the adjustment coefficients are clearly going to suffer. Let's look at performance over time. Multiple time trends. If various subsets of the inventory are trending differently over time, hot versus not, is it appropriate to use one model? So this chart illustrates the time trends, the 66-month time trends for various parts of Philadelphia. Notice that no two of them are alike. Imposing one time trend across the entire inventory will result in time adjustments that are inaccurate for each of these areas. Consistency of data quality is a driver. If your data has not been consistently captured and maintained, areas with less data quality or poorer data quality will tend to degrade performance of the entire model if there's only one model. In other words, they're going to pull the entire model down. Do you want to do as well as possible in as many places as possible and limit your errors to only a small number of places? So by splitting into multiple models, the areas that have really good data, you're going to get better performance out of them. And the areas where there's poor data, it's only going to affect those models. And that may be something that you want. Efficiency and standardization. Do you have the time and manpower to manage multiple models? This is a very real limitation for many of us. Would you benefit by having one standard approach to apply across all the properties? So if you have multiple modelers, they could each be writing their own slightly different variations of the code using different transformations, and that means that you don't have a standard approach across the entire evaluation process, and that might not be desirable. But on the other hand, being able to tailor each model to the data for that subset of properties and make it the most efficient and the most accurate and precise for that subset of properties might be something you want to do. So it's like how you shop for clothes. Do you go to the one-size-fits-all store, or would you prefer to get something that's tailored specifically for you? What type of model structure do you use? Some model structures are more capable of handling diverse populations than others. So linear models, there's only going to be one fit line. In nonlinear models, you can get multiple fit lines and they can be curved. In machine learning, AI, or gradient boosting models, there's no fit line. So we built a GBM, and the performance difference between using only one model and multiple models really wasn't all that much different, because the structure of that model can really account for pretty much all variation in the inventory. So maybe the last thing that bears consideration: who's the boss? We all work for somebody. And when you have to negotiate buy-in from multiple sources, it may not be your choice to make whether you use one model or many models. Somebody else may make that decision for you. Whatever choice is going to be made, you may need to live with it for a long time. So make your best arguments for whichever approach you want to take right from the start. Comparing results. When you're going to make your decision, you want to test both approaches. Try one model, try a few different models, and see which one seems to be working better for you. Which approach gives you the more sensible set of constants and coefficients? Which one has the best rate, produces the best ratio statistics? Which one is performing better based on your model diagnostics? Which one has the better accurate? Which approach gives you better accuracy and quality of predicted values? So you want to test and test and test so that you're making your decision from an informed place and not from, just, oh, well, I think one works, or, oh, I think I need many. Try it and really measure the results so that you're making a qualified decision. So here, in closing, are some general rules to follow. Try not to mix markets in one model. Try not to set your models up so that you're going to be producing confused coefficients. Don't mix multiple time trends in one model. Maximize representation. So what's the verdict? Well, there's really no definitive answer. You can make good arguments on both sides of this issue. But I think that your principle should be that you want to use as few models as possible, but as many as you need. There's going to be a balance to be struck. Don't guess. Test all options and then stay with the approach that you choose. So since modelers like equations, I'll leave you with this. The optimum number of models equals the number of observations divided by the number of submarkets raised to the power of data quality multiplied by available manpower times the number of time trends times the log of the performance metrics times the boss's decision raised to the power of either 0 or 1. Thanks for listening in. I hope this information has been helpful to you.